This is the 17th video in our series on topology, and in the previous video we looked at compactness in the real line and thus compactness in Rn. And we showed that a set in Rn was compact if and only if it was closed and bounded. We actually just showed it for the real numbers, but then we've got a result regarding products of compact spaces that kind of like pulls everything together from there. Okay, well, next up what we want to do is maybe see if this can be generalized a little bit by asking the question, well, does closed and bounded in a metric space imply compact? And in fact, it doesn't. And we'll see that via the following example. So let's recall that C01 is going to be the set of all continuous functions from 0, 1 to R. And then, well, there are a number of different metrics that you can put on this space. The metric we'll take will be the maximum metric. And by that I mean the distance between a function f and a function g will be the maximum of the absolute value of f of x minus g of x as x runs through all of the interval from 0 to 1. And you might say, well, how do we know that that maximum exists and we don't just need the supremum here? Well, we know that the maximum exists because this absolute value of the difference is a continuous function, and it's a continuous function with a compact domain, and we can use the extreme value theorem to give us, well, a maximum. Okay, great. Now, next up, we want to consider this set that we'll call B, and that's going to be all continuous functions, so that the difference from that continuous function to the zero function is less than or equal to 1. So kind of in other words, this is going to be all continuous functions whose absolute value is always less than or equal to 1. Now I'd like to notice that this is clearly closed and bounded. Well, it's bounded by definition. And then why is it clearly closed? Well, this is a closed ball in a metric space. And well, you can prove that this is closed just the way that you'd prove any closed ball in a metric space is closed. And I think we've even done that before. So anyway, we're just going to take that this is closed and bounded and now prove that it is not compact. So that's in a stark contrast to what's going over here in Rn. Okay. So what do we need to do to show that it's not compact? Well, by the definition of compactness up here, we need to find an open cover that does not admit a finite subcover. But in fact, our proof will go by way of contradiction. And what I mean by that is we're going to start with an open cover, assume that it's compact, and thus we have a finite subcover, and show that that leads us to a contradiction. Okay, so for all f inside of C01, let's maybe set u sub f equal to all functions g, well, they've got to be continuous functions on the interval from 0 to 1, so that the distance from f to g is less than 1/2. So in other words, these are simply open balls of radius half centered at the function f. Now notice that we're adopting the geometric terms for open ball, closed ball, that kind of make a lot of sense in R2 and R3 and even Rn. But there's not really a nice geometric representation of what this means inside of a function space. I mean, you can kind of think of it as some sort of spherical-ish object in a function space, but again, it's not something that you really want to worry yourself with visualizing. Okay, and so now let's note the following. So I'm going to put all these things together into this thing that I'll call script u. So that's going to be uf as f runs over everything in our function space. And that this is an open cover of, well, the entire function space. think it's pretty clearly an open cover of the entire function space because notice that UF contains F for all F in the function space. So needless to say, we're able to get one of these U sets that contains every function. Okay, so now let's note that since it's an open cover for the entire function space, that means it's also an open cover of B. Well, if it covers the whole thing, it's going to most definitely cover this subset B. And now we're going to, apply our by way of contradiction argument to get a finite subcover. So let's suppose that UF1, UF2, all the way up to UFN is a finite subcover. Okay, nice. And now the idea here is to build our contradiction, we're going to also consider a family of functions. And those family of functions will be called GIX. And G sub I will be defined by the sign of 2n minus I times pi times x. And, well, let's also note the following, that since the sign of theta for any value of theta is always between -1 and 1, that tells us that GIX is inside of B for all I. Because the entry fee to be inside of B is that your function has to be between -1 and 1. I think that's pretty clear by our definition of B up here. But now let's notice the following. So since B is inside of UF1 union all the way up to UFN, but now since we've got a finite subcover for our set B, and every one of these GIs in it is in our set B, and there are infinitely many GIs, notice that this I is defined for all natural numbers. I guess I didn't write down here that it's defined for all natural numbers, but it is. So, well, let's take a bit of a summary first. So we've got infinitely many functions GI that are all inside of B, but B is decomposing into this finite union. So that means that, well, one of these sets right here has to have infinitely many of the GI, but we don't actually need all of that. We only need one of these sets right here contains 2 of the GI, which is most definitely true because we're taking infinitely many functions and putting them inside of n boxes. So at least one of the boxes will have 2 functions by the pigeonhole principle. Okay, so in other words, what we can get out of this is there exists, I'll say K, L, and J such that GK and GL are both inside of UFJ. Again, those are our 2 functions inside of the same set. But now we're about to get to our contradiction. So let's observe that the distance from GK to GL by the triangle inequality is less than or equal to the distance from GK to F sub J plus the distance from F sub J to GL. Again, that's just by the triangle inequality, taking our third point, if you will, to be the function Fj. But let's see, being inside of UFJ means these 2 functions are within 1/2 of a unit from Fj. That's a definition of our set U sub F here. So that means this whole thing is strictly less than 1/2 plus 1/2 or 1. So let's look at this here. We've got the distance between GK and GL is strictly less than 1. And now we're about to see that that is, well, actually unattainable, or that is impossible. And we can do that with the following. Let's, without loss of generality, assume that K is less than L. I maybe should have been clear here that k is not equal to L because we wanted two different functions inside of this UFJ. But if they're different, one of them is smaller than the other one, and we might as well take the k to be the smaller one. And then next up what I'll do is I'll set x equal to 2 to the L minus n minus 1. And now here's where everything kind of starts to fall apart. Let's look at g sub k of x. But notice that g sub k of x is going to be equal to the sine of 2 to the L minus k minus 1 times pi. That's just inserting that value of x into our function gk, which is defined like this right here. That since L is bigger than k, this power of 2 is bigger than or equal to 0. But if this power of 2 is bigger than or equal to 0, we have sine of an integer value of pi. But sine of an integer value of pi is 0. Okay, so now on the other hand, let's take g sub L of x, and let's observe that that's going to be equal to the sine of, well, when all is said and done, pi over 2. So I'll let you throw that value of x into our g sub L, again, as defined right here, and see that it simplifies down to sine pi over 2. But that's equal to 1. But note that putting these two things together, that tells us that the distance between gk and gl is bigger than or equal to 1. Because, well, we found a place where it's equal to 1. Well, that doesn't mean that it can't be larger than 1, but we've already got a problem. And we've already got a problem because of this. Let's notice that in this magenta underline, we just showed that the distance from gk to gl was strictly less than 1. And then by our careful choice of the value of x, we just showed that that distance is bigger than or equal to 1. But of course it can't simultaneously be strictly less than 1 and bigger than or equal to 1, so that's our contradiction. And that contradiction leads all the way up here where we made an incorrect assumption. We are in fact not able to find a finite subcover. So if we're not able to find a finite subcover, that means that B is not compact. And that, shows us that in a metric space, you don't necessarily have this kind of notion of compactness being the same as closed and bounded. That's something that happens in Rn, but not in this space. Okay, so next up I want to look at a little twist on the idea of compactness. Now we want to look at the notion of limit point compactness. And so the definition goes like this. X is said to be limit point compact if every infinite subset A of X has a limit point. But notice that we could write that as follows. So here we've got a set A, which has infinitely many elements. So the cardinality of A is infinity. That implies that A prime is not the empty set. Recall that A prime was the set of limit points of A. Notice here, this does not guarantee that the limit point is inside the set. It just has a limit point. Okay, so let's see what we're going to prove now. So we're going to prove that if X is compact, then it's limit point compact. And then we're going to give a counterexample for a set that's limit point compact, but not compact. Okay, great. So how are we going to do this? Well, let's suppose X is compact, and then we'll prove like the contrapositive of the definition of limit point compactness. And so we'll assume that we have A inside of X has no limit points. And now, well, let's look over here. If A has no limit points, then in order to be limit point compact, A must be finite. So that's what we're trying to do here. We're trying to show that A is finite. Okay, so let's get going. So let's observe that for all points A inside of A, we can find an open neighborhood of A. So we have an open neighborhood U sub A of A such that the following is true. U sub A intersected with A is just the singleton A. And now why is this true? Well, this is because A has no limit points. So let's recall that a limit point is something so that every open neighborhood of that limit point intersects the original set in another place other than the limit point. But if there's no limit points, then it should be possible to find an open neighborhood for everything inside of A that intersects A in a single point. Okay, cool. So now let's also note the following. So since A prime is empty, because we're assuming it has no limit points, that means that A is equal to A union A prime, because that's just A union the empty set, which is the closure of A. So that tells us that A is closed. So taking a step back for a little bit, we've found these goofy open neighborhoods of every point in A that intersect A at only a single point. We've found that, and then we've also shown that A is closed. But if A is closed, that means that its complement, x minus A, is open. But, well, now what are we going to do? Well, we've got a bunch of open sets. So this is one of the open sets, and then we've got a collection of open sets U sub A. And, well, we have the compactness of X. So we probably want to use the compactness of X with these open sets. But we need these open sets to be an open cover. But they, in fact, do form an open cover. So let's set script U equal to the collection of all of these U sub A's union with our set X minus A. So now, why is this an open cover most definitely of X? Well, notice that X breaks down into two pieces, the elements of A and the elements outside of A. Well, notice that the elements outside of A are all inside of this set, the complement of A. But then the elements inside of A, well, each of them is connected to their own U sub A, and it's inside of that U sub A. So, well, I think that is sufficient to argue that this is an open cover of X. Okay, good. But now let's find a finite subcover. And we're guaranteed to have a finite subcover because X is compact. And let's say that finite subcover is U sub A1, U sub A2, so on and so forth. That means I should be able to take this union of all of these U sub A1, U sub A2, all the way up to U sub AN, and maybe X minus A, and get all of X. So that's it being a finite subcover. Now, does this finite subcover necessarily have this X minus A? Well, no, it doesn't. But we can just union that on, and that won't change anything because it's producing the whole space anyway. But if we've got this union is equal to X, if we pull apart this part right here, which is the complement of A, then that means that A is contained in the rest of the union. So U sub A1 all the way up to U sub AN. So something like that. So now what I want to do is observe that A is equal to A intersect A. Nothing really is going on there, but then I want to intersect everything that is going on to the right here. So I'll intersect this big union with A. But then the intersection will distribute over the union and give us U sub A1 intersect A, unioned with U sub A2 intersected with A, union all the way up to U sub AN intersected with A. But then by the way we chose these open neighborhoods up here, that's simply equal to the singleton A1 unioned with the singleton A2, unioned all the way up with the singleton AN. But if you union a bunch of singletons, you're just going to get this set A1 up to AN. But look at what we've got here. We've got A is a subset of a finite set. But if it's a subset of a finite set, then in fact, A itself must be a finite set. And I think you can argue pretty easily that A is in fact exactly equal to that set. But all we need is that it is a finite set, which means we've proved that if X is compact, it satisfies the contrapositive of the definition of limit point compactness. But of course, the contrapositive is equivalent to the normal definition of limit point compactness. So to kind of put everything together, we show that if you start with a compact space, that space is also limit point compact. Okay, so now let's look at a counterexample for the converse of this theorem. So now for our example that limit point compactness does not imply compactness. And this example is kind of goofy because if your space is, nice enough, well, limit point compactness will imply compactness. But we're actually not going to look carefully at what you need to add to your space to make it nice enough. I'll let you guys look into that if you want to. Okay, so here's what we're going to do. We're going to take Z with the discrete topology. So let's recall in the discrete topology, every set is an open set. And we're going to take the set containing 0 and 1 with the indiscrete topology. Let's recall in the indiscrete topology, the only open sets are the empty set and the entire space. In this case, the space is simply this doubleton 0, 1. And now what we want to do is consider a set X, and this set X will be Z cross 0, 1 with the product topology. And then, well, let's just recall that the product topology will have a basis of open sets which are open in here, cross open in here. So now what we'll do is take any non-empty subset of X. So there we've got the empty set is not equal to A, that is a subset of X. And then what we want to do is pull apart or pull out any element of A. So notice that any element of A will have the following form. It'll either be n, 0 or it'll be n, 1. So maybe without loss of generality, we'll say that n, 0 is inside of A. Okay, nice. Okay, now what we'll do is take any open neighborhood U of n, 1. So just to maybe note what we're doing here, we have, without loss of generality, assumed that n, 0 is the one of these things that's in A, just by swapping 0 and 1 if we needed to. And now we're taking any open neighborhood of its companion, which is n, 1. And now I'd like to note the following, and that is the smallest open set containing n, 1 is the singleton n cross the set containing 0 and 1. Well, and why is that? Well, the smallest open set in Z containing n is the singleton n. I think that's pretty clear. And we know that's open because we're in the discrete topology. But then the only non-empty open set in the indiscrete topology here is the entire thing. So that's how we get this smallest open set containing n, 1 is, well, that thing right there. But let's notice that this is equal to the ordered pair n0, the ordered pair n1. And putting this all together, that means that we know this n, 0, n, 1 is in fact a subset of U. But now what I'd like to do is the following. Now let's note if we do an intersection of U with A, well, we're going to most definitely contain the point n, 0. So let's see what we did here. Well, we started with an element of A. We took an arbitrary open neighborhood of maybe the companion of this element, and we showed that that open neighborhood contains our original element. But notice it contains our original element that is not what we're forming the open neighborhood around. But that means that n comma 1 is a limit point of A. So in other words, it's in A prime. Now, well, what did we just show here? We actually showed something a little bit stronger than limit point compactness. We showed that any non-empty set has a limit point. So in other words, if we've got any non-empty set, the set of limit points is non-empty itself. Well, if any non-empty set has a limit point, then definitely any infinite set also has a limit point, meaning this is limit point compact. Now let's just prove that it's not compact. Okay, so we just finished showing that this space is limit point compact. Now we'll show that it's not compact. And this is actually pretty straightforward. Let's take the following open cover, which we'll call U, and that'll be the collection of subsets of the form, let's see, n comma 0 and n comma 1, as n runs through all integers. So I think it's pretty clear that this is an open cover. We argued why this set right here that we're building this collection out of was open. It clearly covers X, because if you take n comma something, it's going to be in one of these. And also it has no finite subcover, because if it had a finite subcover, then necessarily Z would be a finite set. But we know that Z is not a finite set. So we've just shown that this space X that we've constructed is limit point compact, but not compact. Okay, now I'm going to leave you with some exercises. So here's some exercises that mimic some of the things that we proved about regular compactness. So let's suppose that X is limit point compact. So first, if f is a continuous function from x to y, is the image f of x limit point compact? Recall that we proved that if we started with regular compact, then the image was compact. Next, if A is a closed subset of X, is A limit point compact? Recall again, we proved that closed subspaces of compact spaces were compact. And then finally, if X is a subspace of Z, where Z is Hausdorff, is X closed in Z? Again, we proved that if we had a compact subspace of a Hausdorff space, then that subspace we started with was, in fact, closed. So these are all kind of in parallel to those results that we proved about compact sets. And that's a good place to stop.